Hello, this is Josh Young from Tarleton State University. This is my legacy project. I will be doing problem 4.22. Some theory and things to know. Useful out of this chapter, of course, chapter 4, linear dielectrics, Laplace's equation, and then to solve this problem we'll need to know partial differential equations and ordinary differential equations. Here's the problem statement. A very long cylinder of linear dielectric material is placed in an otherwise uniform electric field E0. Find the resulting field within the cylinder. The radius is A, susceptibility chi E, and the axis is perpendicular to E0. Process. We are going to draw a picture, list the boundary conditions of the problem, and then we're going to go ahead and solve Laplace's equation for the problem, apply those boundary conditions, and solve for a solution. Here's our picture. We have our axis on an infinitely long, well, not infinitely long, just perhaps a very long cylinder. It's on the z-axis, as you can see here. Here's our radius A, and the E field is going perpendicular through the cylinder. Let's go back to this slide. Let me give you the last boundary condition. V out is equal to negative E0 S cosine phi for S much greater than A. Okay, so here's Laplace's equation, cylindrical coordinates. This is in the front cover of the book, generic equation. So we'll write that down. Since there's no internal charge, we're going to set it equal to 0. And we're going to go ahead and let V equal x of S and y of phi. Okay, Laplace continued. So what we're going to do now is we're going to plug in those two functions, x of S and y of phi. Here's what it looks like in this first picture, and then we're going to go ahead and multiply through by 1 over x of S times 1 over y of phi. Okay, separation of variables. So we're going to go ahead and multiply through by s squared, giving us this picture here on the top, and then we're going to set both sides equal to negative k squared. As you can see in the graphic, that should be negative k squared, but it's k squared. Typos, I suppose. Sorry about that. R squared plus k squared equals 0. R equals plus or minus the square root of negative k squared, which means we have cosines and sines, and that's the solution listed there in the bottom picture. Okay, k equals 0, so s dds times s dx ds equals 0. Dx ds equals c over s, so x of s equals c1 natural log of s plus c2. Okay, so what we're going to do now is put both functions together, v equals xy, and that is listed there. We're going to go ahead and apply the third boundary condition. V out equals negative E0 S cosine phi for S much greater than A. And here's it applied in this picture here. Then we're going to go ahead and state V in. Okay, now we're going to go ahead and apply boundary condition 1 on xy plane. V is equal to 0. And it's listed there, shown in the picture. Okay, and these are a little bit out of order. I know we did boundary condition 3, 1, and then 2. It's just how the math flowed. So here is boundary condition 2. And we're going to go ahead and simplify some of these constants so we can start solving for them. Okay, now we're going to go ahead and solve for the constants. So A1A equals negative E0 A plus A inverse C1. 2 equals epsilon r, A1 equals negative E0 minus a to the negative 2C1. We're going to manipulate these equations, push them around, just as it's listed here. You can see clearly how that goes. And then right down here, we solve for A1. And we have E0 over 1 plus chi E over 2. Okay, and here's the final solution. So Vn S phi equals negative E0 over 1 plus chi E over 2. S cosine phi. S cosine phi, of course, is x, and if you look at the partial, our solution is in the bottom right. And have a good Christmas, Dr. Storr.